This is lecture video 39, and in this video we will cover solids of revolutions and how to find the volumes of them by using this method. Okay, what's the solid of revolution? The solid generated by rotating or revolving a plane region, like this one here, about an axis is called a solid of revolution. So this solid is obtained by revolving this region around x-axis. So revolve the region, shaded region around x-axis, then you will obtain this solid region, and it is called the solid of revolution. And to find the volume of a solid like this, we only need to observe that its cross-sectional area, which is this shaded part, this is the cross-sectional area of it. Its cross-sectional area is the area of a disk with radius r. Disk with this radius. Why the radius is r of x? Because you see this part is the radius of this disk, which is the cross-sectional area for this area, solid of revolution. And let's call this part as the radius. Why? It depends on x. For any x point on your x coordinate over any x point, the radius is determined by the curve square root of x, right? That's why it is the radius depends on x. And the area, cross-sectional area of this disk is obviously pi, the radius square, and radius is given by r of x here, which is determined by this curve, okay? And if you want to find the volume here, the volume of this object, this solid, you need to integrate the area of cross sections over x-axis from where to where? Obviously from 0 to 4. This is the interval of integration from 0 to 4. So let's compute this computation. What is a of x? It is pi times radius square, and radius here is given by this formula, square root of x. That's why it is square root of x square, so pi x, right? Okay, I will just want to express it. We will do nice computations soon. So this part is the radius square part. Maybe I can rewrite it like this. Pi times r of x square. So from 0 to 4, pi times square of this thing. Okay, so this technique is called disk method, and it gives us the volume of solids of revolution. And here the important thing is that the cross sections are in fact perfect disks with radius r of x shown in the figure, right? Okay, so let's look at this example again, but before the example, this is the summary of what we have covered above. Volume is given by the integral of the cross sections, and cross sections here are the disks with this radius. That's why their area is expressed like this. Okay, now we were dealing with this example. What we have done above is to revolve this region around which axis? We revolved it around x-axis. So if you do this revolution, so you are just turning this planar region around x-axis to obtain this three-dimensional shape. And if you concentrate on the cross sections of it, you see that the cross sections are in fact the disks with this radius. So we already covered this above. Areas of the cross sections are pi radius square, so pi square root of x square. Radius is given by the curve, and the interval of integration is this part. That's why now we can compute the volume computation. Volume is given by this definite integral, you will integrate the areas of cross sections from 0 to 4. Okay, that's why the integral looks like this now. Dx, so it is from 0 to 4 pi x dx, and so now integrate, it is x squared over 2 from 0 to 4. And if you insert these upper lower boundaries, take the difference, you will find 8 pi as the volume. Okay, let's look at the next example. Again, our region to be revolved around x-axis is this region. Then if you imagine it, you will obtain, by the way, also the axis of revolution is changed here from x-axis to y equals 1 line, which is here. Now you are revolving this region around y equals 1 line, not x-axis, but here. Okay, let me emphasize that. Revolve the region given here in blue around not x-axis, but y equals 1 line. And this you will obtain. Okay, now we want to compute the volume by using this method. That's why we will be integrating the areas of this disk, cross sections. Let's try to express its area in terms of x. Okay, let's concentrate on the radius. This is the axis of revolution for us. Revolution. And that's why this part is our radius now, r of x. And we want to compute this length. You know, the length from here to here is what? It is determined by this curve. So it is this much square root of x. And the length from here to here, this length is 1. So r of x is in fact what remains. So if you take the difference of this length with this length, you will find your radius. So radius is, this part is given then by this difference, right? Okay. So this is some fixed difference with as 1, because this is y equals 1 line. From here to here, it is your curve. It is determined by your curve. The curve is y equals square root of x. That's why radius is given by this difference. And once you express your radius in terms of x, you are almost done, because we will be integrating this, where the radius is given by this square. Okay, then the volume of this solid object obtained by revolving this region around y equals 1 line is given by the integral, this definite integral from where to where. Again, you look at x coordinate to find the boundaries for x, right? So from 0 to 4, 0 to 4, we are integrating this. Okay. So boundaries for x is, sorry, this is not 0, but 1, you know, it is 1, not 0. From 1 to 4 on x-axis is the interval of integration. Now, let's compute the integral. Okay, from 1 to 4, pi can be taken out. Let's compute the square first. It is what? It is x minus 2 square root x plus 1 dx. Now we all have power functions here. I can integrate them easily. X squared over 2 minus, this is x to the power 1/2. So you add 1 to the power, divide by the same power plus x. And then you will insert your upper lower boundaries for this integral to find this result. Okay, this is the volume of this solid object that is obtained by revolving this region around y equals 1 line. Let's move on. Now we will cover the same kind of idea, same type of idea with respect to y-axis, okay? So the volume of the region revolving, okay, you see everything is with respect to y now. C and D are the boundaries for y-axis because you're integrating with respect to y, and A, the cross-sectional area will be given in terms of y. That's why the radius will be expressed in terms of y. So we are doing the same thing, except that we are integrating over the y-axis. So let's try to understand why we have such a formula for the volume by using the disk method, but with respect to y. Look at this example. Here is your region, and you are revolving this region around y-axis to obtain this three-dimensional solid object. Revolve the shaded region around not x-axis but around y-axis. This is the crucial difference now. And that's why you will obtain something like this, obviously, and the cross sections are now not vertical as in the previous example. You see here the cross sections are vertical discs, but now you slice your three-dimensional object horizontally. That's why the cross sections looks like this now, horizontal discs. Okay, and you put these cross sections over this arbitrary point y on y-axis, and this is your radius now. And you need to express this radius in terms of y, not x, but in terms of y. Okay, so what is it? You know, this is your curve given by this formula, x equals 2 over y, and okay, also in this picture we can work. So for some arbitrary y on y-axis, which is your revolution axis, we need to find where we hit on x-axis in terms of y. So to have your image as y, you need to hit this point on x-axis, okay? This point can be expressed 2 over y because, you know, this is the point on your curve, and this curve has this equation, x equals 2 over y. So for the image y, you need to hit this point on x-axis, which is given as 2 over y. So this is your radius. Then, you know, this is the radius of the disk as it can be seen here, and it is given by this formula. So you hit this point on x-axis, x is given by 2 over y, so it will be your radius. After you express your radius in terms of y, the rest is so standard. To compute the volume, you need to integrate the area, the cross-sectional area. Okay, I can also write it here. Area of this cross-section in terms of y is pi ry squared, so pi 2 over y squared. So you will be integrating the area of cross-section, which is written in terms of y, over y-axis, not x-axis, but y-axis. So this is your interval of integration now from 1 to 4 on y-axis. Everything is with respect to y. We should be careful about that. Okay, let's complete the computation. From 1 to 4, a of y is pi radius squared. Where the radius is expressed in terms of y. So radius is given as 2 over y squared dy. Okay, let's compute this integral. We are integrating from 1 to 4. Pi goes out. It is 4 over y squared dy. And you know, this part can be rewritten as pi is out 1 to 4. 4 times y to the power minus 2 dy. So this is a power function. You can easily integrate it. You know the rule. Add 1 to the power, divide by the same power, and then you insert your boundaries for y. Y is changing from 1 to 4. Insert these boundaries, take the difference to find your result as 3p. So I stop here. We covered this method in this lecture video.